Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we will be learning about the AAS theorem and the HL theorem. To get started, let's look at the following figure. Here we can see that angle A and angle X are congruent in both of these triangles. Also, angle C is congruent to angle Z, and we have segment BC congruent to segment YZ. The question is, are these two triangles congruent? Why or why not? So now we want to think about all the postulates that we have available if we can somehow prove these two triangles congruent or not. In one of our previous videos, we learned that there are three postulates to prove triangles congruent, namely the SAS postulate, the ASA postulate, and the SSS postulate. So for our problem, it seems like that we might use the ASA postulate. Let's look at it. So in order to use the ASA postulate, it says here that if two angles and the included side of one triangle are congruent to the two angles and the included side of another, then the triangles are congruent. So the key word here is included. What does it mean, included? Well, it means that the side has to be in between those two angles as shown here in the diagram. But for this particular problem, that is not the case because the side, we can see side BC here, is not included, is not in between those two angles. And also segment YZ is also not included or in between those two angles. So are these two triangles congruent? At first, it seems not. But let's think about this further. The fact that we have two angles in triangle ABC congruent to two angles in triangle XYZ, namely, angle A is congruent to angle X, and angle C is congruent to angle Z, then what can we say about the third angles? Must they be congruent as well? Well, the answer is simply yes. Therefore, angle B is congruent to angle Y because of the AA postulate. Remember, the postulate states that if two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. So according to the diagram now, as you can see, we can see that angle B and Y have to be congruent as well. So can we now use the ASA postulate? And the answer is yes, because now we have two angles and the included side congruent to two angles and the included side of the other triangle. So now we can say that triangle ABC is congruent to triangle XYZ because of the ASA postulate. So if we think about this, we have just proven something that is always going to be true. That if you have two angles and the non-included side of a triangle congruent to two angles and the non-included side of another triangle, then it always must be true that the triangles are congruent. And the fact that we have just proven this, and it's always true, it now becomes a theorem. And also, since we have two angles and a side, we now want to differentiate that from the ASA postulate and just call it the AAS theorem. And notice that AAS is written this way because the side is not in between the two angles like the ASA postulate. So let me define the AAS theorem at this point. So the AAS theorem states if two angles and the non-included side of one triangle are congruent to the corresponding parts of another triangle, then the triangles are congruent. So in a proof, it is sufficient to just write AAS theorem. You do not need to write out the entire definition of the theorem itself. So let's look at another example now. Let's say we have two triangles as shown in the figure in such a way that they share segment BD. So that means that vertex B and D do match up. How can we prove that these two triangles are congruent? Well, another piece of information is that we know that segment BC and segment AD are congruent. We also know that angle A and angle C are right angles, okay? We don't know if segment AB and CD are congruent or parallel, so we can only work with what we have. How do we know if these two triangles are congruent? Could we maybe use the ASA postulate? The answer is no, because we don't have two angles that are congruent to angles of the other triangle. What about the SAS postulate? Can we use that? Well, in order to use it, you need another side, right? But even if we know that this side over here is congruent to itself, we do have two sides and an angle now. However, the angle is not included. In this case, we would have to know that this angle is congruent to this angle, right? But it's not the case. We only know that these two angles here, A and C, are congruent. So it turns out that we cannot use the SAS postulates either. What about the SSS postulate? Would that work? Well, that doesn't work either because we only have two sides. We don't know if segment AB and CD are congruent. So therefore, it doesn't work either. And what about the AAS theorem that we just discovered? Well, for the AAS theorem, we need another angle, and we don't have it. And unfortunately, that doesn't work either. But it turns out that these triangles still have to be congruent. There's no postulate or theorem that we can use so far. So if we cannot use anything, then we must somehow construct something else in this diagram in such a way that we can now use one of the known postulates. Okay, so let's do that. So the first step here is we want to draw point E somewhere on ray CD or DC such that segment AB is congruent to segment CE. So let's draw that out. Now, from the diagram here, what can we say here? So there are many things we can state here. Well, we know that angle BCD is a right angle. Well, what can we say at this point? Well, if you look at triangle BAD and triangle ECB, we can now say that they're congruent, right? And the reason is the SAS postulate. Notice that here, I'm actually skipping a lot of steps because I'm not doing a formal statement reason table, but this is kind of like a brainstorm. So normally all reasons need to be provided as well. For example, for step 1 and step 2. I can also show you at the end how a formal statement reason table will look like. But nonetheless, let's continue with our thought here. Now that we know that the two triangles are congruent, how does that even help us? Well, we can use corresponding parts of congruent triangles to say that segment BD is congruent to segment BE by the corresponding parts of congruent triangles are congruent. So let's denote that in the diagram. Let's now look at triangle DBE. What kind of triangle is that? Well, we know that two segments are congruent, segment BD and BE. So that means that triangle DBE is an isosceles triangle. So what do we know about isosceles triangles? That not only two of the sides are congruent, but also the angles opposite those sides are congruent as well. And that is actually, as you remember, because of the isosceles triangle theorem. So therefore, angle BEC is congruent to angle BDC. Now, when we prove that triangle BAD is congruent to triangle ECB, as you can see highlighted here, we can also use that fact to show that another corresponding parts of those two triangles must be congruent. As a matter of fact, angle E in triangle ECB must be congruent to angle ABD in triangle BAD, as shown in the diagram now. Now, if we look at our 6th and 7th step, what do we notice here? Well, we notice that angle BDC and angle ABD are both congruent to angle BEC. Therefore, we can conclude by either the transitive or substitution postulate that angle BDC is congruent to angle ABD. So let's highlight that in the diagram. Here, now we see that angle BDC is congruent to angle ABD. So the question again is, are the two triangles congruent? Basically, triangle BAD and triangle CDB. Are they congruent or not? Well, the answer is yes, because now we have sufficient information to prove it. If we look at the diagram, here we have an angle that is congruent to this angle. Then we have another angle that is congruent to this angle that we have just proven. And we also have a side that is congruent to the side in the other triangle. So for example, let's pick this side over here, the one that is being shared by both of the triangles. Now, regardless, we can now use the AAS theorem that we have just proven in today's lesson to prove that these two triangles are congruent. And the reason is because the side is not included or in between those two angles. Therefore, we can say that triangle BAD is congruent to triangle DCB because of the AAS theorem. And we have just proven that these two triangles are congruent. Also, here is a detailed statement reason table for the proof if you're interested in it. Let's now go back here and come up with a theorem that is always going to be true in these types of scenarios. Now, in this original problem here, we had the following given. We were given that the legs were congruent. We were also given that the hypotenuse of this triangle was congruent to the hypotenuse of the other triangle. Now, why is it okay to call that the hypotenuse? Because here we're dealing with right triangles. So again, this theorem that we are going to develop now only works for right triangles. So it's very important to know that you must have right angles. If not, this theorem is not going to work. So since we're dealing here with the hypotenuse, which is capital for H, and we're dealing with a leg that is congruent to the leg of the other triangle, here we're dealing with capital L, we can now safely call this the HL theorem. Now, what is the definition of the HL theorem? The HL theorem states that if the hypotenuse and the leg of one right triangle are congruent to the corresponding parts of another right triangle, then the triangles are congruent. So in a proof, we can now use HL theorem instead of writing the entire definition. However, it is very important to prove that the triangles are right triangles. So basically, you need to state that you have a right angle in each of the triangles. They don't have to be necessarily set to be congruent, but they just need to be stated that you have right angles, and therefore, by the definition of right triangles, those two triangles have to be right triangles. And then you can use the HL theorem, given that you're proving the legs congruent and the hypotenuse is congruent as well. Let's now briefly look at some examples. It says here, state which congruence methods can be used to prove the triangles congruent. If no method applies, write none. So for number one, which method can we use here? So here we know that two sides are congruent. We also know that two of these lines are parallel. So for example, here we could say that this angle must be congruent to this angle because these are the alternate interior angles and they must be congruent because of the theorem that we have learned in one of the video. We can, for example, also state that this angle here must be congruent to this angle because these are vertical angles and they're congruent. So now we have two angles and a side that is not included. So therefore, we can say that these two triangles are congruent because of the AAS theorem. Notice that here we could have also proven that the other pair of alternate interior angles are congruent and then use the ASA postulate. So there are different ways to prove them congruent. What about number two? For number two, we know that these are right angles on the bottom, okay? Since we know that on the right here we have a right angle, the one on the left must also be a right angle. So even though we're tempted to use the HL theorem, we don't know anything about the hypotenuses, but we also know that this segment is congruent to itself. So now we have a side, an angle, and a side. So therefore, we know that the triangles are congruent because of the SAS postulate. Now let's look at number 3. Again, here we have parallel lines. Do we know anything about the angles? Well, we can use, for example, the transversal in the middle. And we can say that this angle here must be congruent to this angle. Now, again, if we look at both of these triangles, we have two angles that are congruent to angles of the other triangle, and the non-included side is congruent to the non-included side of the other triangle, and therefore we can again use the AAS theorem. Now, for number 4, we again have two angles congruent to two angles of the other triangle, but then we also know that these segments here, this segment here is congruent to itself, which is shared by both triangles. And again, we can claim that both triangles are congruent because of the AAS theorem. Now, if we look at number 5, there are multiple ways to actually prove these two triangles congruent. For example, in this case, we have a side angle side, so we can easily use the SAS postulate to prove them congruent. Can we use a different postulate or theorem? The answer is yes, because we know that they share this segment here. So that is congruent to itself. So we can, for example, use the SSS postulate. In a similar manner, for number 6, we also have that this segment is congruent to itself. And now we can also use the SSS postulate to prove the triangle's congruent. Now, for number 7 here, now we have two right angles. Then we have a leg that is congruent to the leg of the other triangle. And we know that the hypotenuse is congruent to itself. Now, in this particular case, we must use the HL theorem. And finally, what about number 8? Well, in that case, we have three angles congruent to three angles of the other triangle. Do we know anything about the sides? The answer is no, we don't. So it turns out we cannot prove these two triangles congruent, and therefore we are writing none. So that's basically it for today's lesson. Again, thank you for watching and have a wonderful day.